to the second talk of the morning. We will have Gabriel Cuomo speaking about impurities with a cusp. Please, Gabriel, take it away.
Okay, so thanks a lot to organizers and for putting together again this wonderful workshop and for inviting me. So this will be based on a paper that recently appeared on the archive with Hinchen and Zohar Komargotsky. But let me also advertise some, say, complementary but related work by two different groups, my NYU colleagues, Sasha Diatari, Himanshu Kanchandani, Fedor Popov, and Yifan Wang. It's like 2 papers plus an upcoming one. And a nice paper by the King's College group, Peter Krapcher, Radcliffe, and Ritam Singha, that studied the fusion of defects. Okay, so let's see if I know how to use this. So the plan will roughly be in 3 parts. I'm not the third part can be very long or very short, depending on questions. I don't care. So please ask as many questions as you want. So I'll start with a very brief review of defects. Then I'll introduce the object that I'm interested in, the cusp enormous dimension. Also, that part will roughly be for at least half of it a review. And I'll finally present some results for the simplest defect I think that we know of. Okay. So as you think you imagine by now, this talk deals with defects. So what are defects? So I'll be interested in CFTs, and defects are just extended operators in CFTs. And you can take, there used to be a picture here. Okay, I'm going to redo it. There are 2 viewpoints you can take when you think of a defect in a CFT, or in a QFT in general. So let's draw schematically our space, say RD, and our defect that in my talk will be 1-dimensional. So now you can quantize your theory in 2 ways. The first thing you can do, you can imagine slicing times like this. Then the defect acts as a moment in time, and therefore the defect is an operator acting in a Hilbert space, obviously. So D is some non-local operator. The second viewpoint you can take, instead, which is more useful, is to quantize in time slices such that at each moment in time, you hit the defect once. In this case, it's more useful to think of the system given by the QFT plus the defect as a new system that you call defect quantum field theory. And the intuition here is that you have your bulk Hamiltonian, and your full Hamiltonian will be the sum of the bulk Hamiltonian plus an Hamiltonian of the impurity or defect, which will be localized on a 1-dimensional space, plus some function, plus some operator. Okay? So this is roughly the idea. So you have some degrees of freedom living there with their Hamiltonian, interact with the bulk, and they modify in a local way the Hamiltonian. Okay. So generically in CFTs, this second viewpoint is the most useful one. And to understand this, it's good to review for you what is the definition of defect CFT. So let's take again our line defect and place it on a straight contour. By locality, we can deform it how we want, but let's focus on the straight contour. Now, geometrically, the maximal symmetry group, the maximal symmetry subgroup of the conformal group that this configuration can preserve is given by a SL2R conformal. What did I do? Good. By SL2R conformal transformations along the line and rotations around it. When this happens, we say that the defect quantum field theory in question, assuming that the bulk is a CFT, of course, is called a defect CFT or DCFT. So let me stress one thing if you've never thought about defect, that this statement is not a trivial statement about the geometry of the defect. It's a statement about the dynamics of the defect. So the defect has its own degrees of freedom that live on this 1-dimensional or 0-dimensional subspace in this case. And they can interact with the bulk, with their couplings, and this coupling can have beta function and run. When I say that the defect preserves this SL2R group, I'm assuming that I sit at a fixed point for decoupling on the defect. We'll soon make this very concrete. So at this point, well, let's say now for a moment that we are in this defect CFT. I want to review for you 3 crucial properties of defect CFTs. So first of all, by the existence of the SL2R group, I can classify operators that live on the defect in terms of representation of SL2R. So I will have some defect operators that are generically different from the bulk operators. That are classified by their quantum number under SL2R. So they are one-dimensional primaries or descendants. So I'll denote them with a hat. For instance, a primary operator will have a 2-point function like this, 2 delta hat. Okay, the usual stuff. And this lives on the defect, of course. I also have bulk operators, and now are bulk operators related to defects? Well, the way they're related to defects is just the bulk to defect is that there exists an OP. It allows you to expand bulk operators in terms of defect operators. So I place some bulk operator here at some distance. Oh, okay. It's going to be challenging. Let's place it here again. Let's try again. Okay, some distance x perp. And then I can expand this bulk operator in terms of defect operators. Delta hat minus delta O hat. So this is just schematic. There are some coefficients here. These coefficients are dynamical. These coefficients here, they depend on the theory. In free theory, of course, this is just a Taylor expansion generically, or can be inferred from Taylor expansion, or well, for the simplest defects in free theory at least. And yeah, so these are new dynamical quantities together with the scaling dimensional defect operators that you want to solve for. Finally, the last bit of review that I'll need for my talk is the existence of a displacement operator. Okay, so what is going on? When I say, I guess this you all know again, but the idea is that the defect breaks translations orthogonal to it. This means that the word identity for translation needs to be modified. So in bulk CFTs, the word identity is conservation of the stress tensor. Here will be modified by a local operator that lives on the defect. I'll call it d hat nu, times the delta function, say, in the simplest case, in x perp. Okay? So you might wonder, this is not the most general modification you can imagine of the word identity when you include a defect, because you can always add a local stress tensor on the defect. But it turns out that when you sit at a fixed point, so for a conformal defect, a local stress tensor for the defect is disallowed. Intuitively, it's because conformal invariance demands that the stress tensor be traceless. The bulk stress tensor is traceless because the bulk is a CFT. The defect is one-dimensional, so traceless stress tensor means no defect stress tensor. In fact, the argument is more general, but for the one-dimensional defect, it's pretty easy. Even this argument has some subtleties, but it's true. So what is the physical meaning of this displacement operator? The physical meaning is that if you imagine considering a defect and adding a small wiggle, then the partition function of the defect on this contour, so this is a contour x mu of tau, this is a contour delta x mu of tau, Then the partition function of the defect to linear order changes by a term proportional to the defect to the displacement operator. Okay, so you are all familiar with the idea that the Ball stress tensor is in linear response theory what tells you how the theory reacts to placing it on a curved space. The displacement operator is what tells you how the theory reacts by adding wiggles on top of your defect. Essentially, it's because you have now a new background field, which is the position of the defect. So, questions so far? Yes. I guess at this level, do I need the log at this level? Let me just think about being too schematic. Yeah, I think it's correct like this. Maybe I'm wrong. Why not? Sorry, I'm doing something wrong. Let me just think. Yeah. So you say if I have the, sorry, it's log. Sorry, I did something wrong. Of course, there is no log here in the numerator, right? That's what you meant. Sorry, I thought that, yeah, of course. Okay, I won't be able to fix this formula, but ask Peter. Sorry, that's the block. So anyhow, so up to mistakes on the log, the point is that if you do a small wiggle, linear response theory tells you add with the displacement. Yeah. Okay, so to complete the review and then start with the real stuff, let me, of course, mention that not all defects are conformal. So, in general, a non-conformal defect is obtained by taking some conformal defect that you can think as a UV defect, pretty much as you do with CFT, and adding a relevant perturbation on top. Where this delta, of course, this delta hat, for the perturbation to be relevant, must be less than 1, because the defect is one-dimensional. Okay? So pretty much like we are often interested in classifying the space of CFTs by studying, possible relevant deformation of free theories or interacting CFT in the UV, we can ask the same question for defect. Can we classify or understand with some degree of accuracy the space of defects, at least in the simplest CFTs that we know of? And of course, this is a well-known question. It has been studied to death in the minimal models, for instance. There is a beautiful classification by Cardi of boundaries. And I think it's still an open question for interfaces in most theories. But we can ask this question more in general, for instance, the Ising model. A relevant example for today is the localized magnetic field. So the physical picture that you should have is to have your Ising model, say, in 2+1 dimension. So it's a quantum critical point. And at each site, you have your spin-half degrees of freedom that interacts with the usual Hamiltonian. And then you do a very bizarre thing. You turn on a magnetic field, but you do it in such a way that it's localized on a single site. Okay? So this corresponds to modifying the Hamiltonian by a term H delta d minus delta 2, in this case, x sigma. where sigma is your magnetic, your primary operator. And in the action, in path integral language, this corresponds to adding to the path integral the following deformation. At a point in space. Okay? The sign, of course, doesn't matter. As you all know, sigma is a relevant operator. It has dimension less than 1, so this is a relevant deformation. Okay? And being relevant means, of course, that this coupling runs. So understanding this localized magnetic field defect means understanding the infrared fixed point of this coupling, the corresponding scaling dimension of the defects, and so forth, so on. Okay. Good. Okay. Questions on the review? No. Okay. Okay. So in this talk, I will be interested in a rather bizarre observable, which is the cusp anomalous dimension. It's an observable which many of you know. It's been studied to death in the context of gauge theories, but not so much in the context of other critical points. And this is a rather bizarre observable in that you do something which doesn't look very physical at first. You take an impurity A on a line, another impurity B, which may or may not be the same. You connect them at a point, and you put them at a cusp of angle theta. So if these two lines are conformal, this is a setup that preserves the dilation group, just because you can take this, the origin, and then you can do dilations. And you can think of this point here as sort of a local operator. In fact, this is a very precise sense. So once you accept the idea, because what is going on? You have a setup that preserves dilation, and you have a local feature. So you should understand this as a local operator. But once you accept the idea that this is a local operator, then you understand immediately that the partition function of this setup will have a log. The logarithm of the partition function of this setup will be like this. So where this coefficient here is the cusp anomalous dimension, so it's the scaling dimension of this cusp. It's called anomalous dimension for historical reason. LIR is some infrared regulator in which you can imagine connecting this cusp to some other cusp or cutting off the length of the line or something. And AUV is instead some UV regulator. And you can think of this dependence on UV as sort of a wave function normalization. When you define an operator, you need to take care of UV divergences, and that's why you have this AUV. More mundanely, it just comes from dimensional analysis. Now, this observable a priori doesn't look, okay, this has been studied to death, for instance, in the context of integrability for supersymmetric lines, there are exact expressions, but I would argue it's interesting also for critical point, and that's because this observable is related to a number of other observables which are more physical, as I'm going to explain. In particular, correlation function of the displacement operator, the fusion of defects, and the corresponding Casimir energy. So let me review this. Okay. So the first comment here, which is again obvious to practitioner, is that if you do a Weierwey scaling of the theory to the cylinder, taking this as the origin, then this cusp maps to a configuration. Let me see, tell me if you cannot see. With two straight lines on the cylinder at angular separation theta. And the cusp anomalous dimension, therefore, is nothing but the ground state energy on the cylinder for this configuration. So this is again familiar because this is a scaling dimension. Scaling dimension corresponds to energies on the cylinder. So there is nothing new. There is a small ambiguity, the one that needs to be taken care of, because once I have a defect, sorry, okay. See if this is going to work now. Yes. Once I have a defect, the defect is always ambiguous. Pretty much like operators are ambiguous by their normalization, defects have their counter terms. The defect is a local object of dimension 1, and so therefore the only the only counter term you can add, oh my god, is a cosmological constant counter term. So you can always redefine the defect by a local integral of the contour of some dimension full scale. This is analogous to wave function normalization in the context of the quark anti-quark potential is called the master normalization. So this means that this ground state energy is ill-defined up to this contact term, up to this term on up to this cosmological constant on the line A and the line B. So if you are a bit more careful and you normalize by the partition function without the cusp, you find that the right formula you need to subtract the ground state energy for two impurities at angle pi with a factor of 1/2, because you have, one single line in flat space corresponds to two lines at angle pi. Since you have one line A and one line B, I put factors of 1/2 here.
Sorry, can I ask a question?
Sure.
So you say that this is ambiguous, but if you're saying this is like a conformal defect and so on, then you would expect it to be like behave nicely under wild transformations, and then or just rescalings, and this contact terms in general will break this property.
So if you have a scheme that preserves value invariance,
sorry?
If you have an explicitly value invariant scheme, you might be able to get rid of this.
But even scale invariance.
Yeah, if you have an explicitly scale invariant scheme, you may forget about these terms. And what's going to happen is that these two terms are going to be 0 generically. Like if you compute, for instance, if you work for the pinning field defect, for instance, in 4 minus epsilon expansion, you don't have any dimension full scale but the sliding scale, which only appears in log, and you will never generate a cosmological constant term. But that's the luxury of the pinning field of the epsilon of dimensional regularization.
Well, but I mean, regularization is just regularization. Once you remove it, it shouldn't matter which one you used.
No, but it's also when you compute partition function of a CFT on a sphere, you generically need to worry about counter terms.
Well, sure, but once you remove the the cutoffs and everything, it's not like you're saying, oh, if you take a CFT and then if you use not DIMREG but something else, but like explicit momentum cutoff, so then it will not be scale invariant.
If you live only in the conformal world and you have an explicitly value or scale invariant scheme, I completely agree with you. Maybe I'm just worrying too much. I'm just saying generically this is we don't have this luxury. If you obtain this defect from some UV defect, you will generate this counter term.
I'm just not sure what, like, I agree that there is an issue, right? Is that if you have a scheme with some explicit scale, then sure, like, by default, it's not guaranteed that whatever definition for a defect you use, that it's going to be the definition which, once you remove the cutoff, is going to give you the scale invariant defect. But I thought part of the whole point would be that you need to figure out precisely how much of this cosmological constant counter term we need to add in order to get rid of that. I'm just not sure why you're subtracting it like in this way. Do you know that? I
mean, okay, if I work in a scheme where this is 0, that's what you're saying. If I work in a, if I do my counter term where this is 0, then I don't need this subtraction, of
Sorry,
course.
this is like AA bar or something? Like that? You mean that when there is a SPI, then there is nothing?
Yes, so this is when...
I see.
Yeah.
I misunderstood what you wrote. Okay, thank you.
Yeah, sorry, Okay, thanks. Okay. Good. So this is the cylinder definition of the cusp enormous dimension. This is the flat space definition. It's good to keep them in mind, both. Okay, so let's keep going. Okay, so the first technical result, which I want to argue, is that this cusp anomalous dimensions satisfy a property which is called concavity. Well, in a property which is concavity, so it's called concavity. So concavity just means that the second derivative of the cusp anomalous dimension is negative. And the strategy for the proof at this point is obvious. So I take the partition function for defects for A and A bar, so the same defects. So this is the setup. I have a defect, generically a defect has an orientation. So yeah, so I should call that A bar, and there is an angle theta. And what I get here is if I do the second derivative with respect to theta, what I'm physically doing, I'm displacing this line here by a small angle, and also this term here by a small angle. I mean, it's a second variation. By rotational invariance, I could think of changing twice this term or changing twice this, but it's more convenient to take this symmetric configuration. And as I told you before, I mean, doing small variation with respect to the position of the defect just means lowering the displacement operator. So it's a matter of completely straightforward algebra to realize that this can be written as an integral, say minus infinity to 0, of the two-point function of the displacement. And okay, so there is some polarization vector, which is just the derivative of the contour. Just me schematic about this. Just the derivative of the contour. So I related this second derivative to an insertion of the displacement here, dj, and an expression of the displacement here, di. Okay? Now, the obvious observation is that this setup admits an obvious reflection positivity if I cut the defect like this. So this means that this quantity has to be positive. So more precisely, additionally, this quantity, this setup preserves scale invariance, and I assume that I am in the ground state. So this means that this correlator must take this form. Function of tau1, tau2. Notice I only have scale invariance, so I cannot use constrain completely the correlation function as we do for conformal primaries usually. So then this becomes, okay. Again, one of the two integrals, you can factorize it in a logarithmically divergent integral that gives you this log. And the second integral becomes an integral over this function x from 0 to infinity of this function f of x. And this function, sorry, yeah. And this is positive. The cusp anomalous dimension was minus this, so the cusp anomalous dimension is concave. To complete the proof, I need to worry 1 second about convergence of this integral. But this is also easily done because I inserted one operator here, one operator here, so they never touch each other. So the only dangerous points are where these operators run to infinity or when this operator touch the cusp, which I should think of as a local operator. But okay, one small thing I have to tell you is that this was the connected correlation function because I took the log. And then by the cusp to defect of P, you immediately find that this f of x the behavior of f of x for x going to 0 is dictated by the OP of one of these displacement going here, and the scaling dimension here must be positive because this is such, it's normalized so that the ground state is energy 0. It's just a statement that once you subtract the ground state, all the rest has higher scaling dimension tautologically. And for x going to infinity, the same thing, with a minus power. So this ensures that this integral converges, and therefore that the cusp anomalous dimension, the second derivative, is negative. Yes? You can do whatever you want. By rotational invariance, you can put them both here, like in the famous paper of Maldacena left. Amit and Maldacena, when they did their calculation, they put them both on the same defect. You can do that. But by rotational invariance, this must be the same thing. And since I want to use reflection positivity, it's more convenient to do this. It's just a small trick. It's like you can think of varying this and then this, and it's like rotational invariance. Nothing changes. It's just a matter of convenience. In the way you're saying it, the reflection positivity wouldn't be manifest. Okay. So this small property will have an interesting consequence in a moment. Okay. Okay, so next I want to discuss some limits of these objects. The first limit is very well known, is the theta to pi limit. So this is the almost straight cusp. And I apologize for integrability people if I use the opposite convention for the angle. In this case, the expansion is pretty obvious, so let me just write it down. So the first term is the term that you have at θ equal pi. At θ equal pi, you're connecting two defects A and B, so it's just the scaling dimension of the defect changing operator. In the case of BCFT, this is called boundary changing operator. Just the state that I connect two different defects. In general, this also corresponds to an operator, and it has a certain scaling dimension. Let me put a 1/2 here. This coefficient beta, in general, is related to this 4-point function. Okay? So this 4-point function is a displacement, defect changing, displacement, defect changing. Because again, on the cylinder, you're just computing 2-point function, the displacement in this configuration with these two line defects, which is created by this operator OAB and OBA. Let me put a not. So in general, we don't know anything about this 4-point function. It's a very complicated object. But of course, in the case where the two defects are equal, for B equal A bar, this reduces to the 2-point function of the displacement, which has a physical normalization because the displacement appears on in a word identity. And in this case, the coefficient beta is given by CD, I think there is a minus CD over 6. I think in the way I chose the arrows, yes. In the way I chose the arrows, B equal A here, yeah. So on the cylinder, it becomes A bar. Sorry. Yeah, and this is, of course, a well-known result. It's just to say that, again, follows by the same trick of inserting the displacement. The other limit, which is the θ equals 0 limit, which is related to fusion and the other papers that I mentioned today. Here, it's more convenient to think on the cylinder. You have a line A, a line B. Let me just put the arrows like this now. And when the two lines are very close, okay, that's just basic physics, just multiple expansion. Two very close points in space, they look like a single point. Maybe a somewhat fuzzy single point. Okay? Sorry, this should be. Okay, I'm not able to erase, you understand. So, in more formal term, what I'm saying is that when you go at small angles, you can think of this cusp anomalous dimension as the expectation value of a defect, which is just the result of the fusion of the two lines. So let me tell you something about the fusion of lines. So the setup is the following. I have a line A, a line B. Actually, let me put a bar because I changed the reversal here. Now, the formal statement, I think, is most conveniently written in this way, and then I'm going to elaborate what it means. With some schematics. C of 0. Okay, so there is here a factor. There is some schematics. Okay, so what I'm saying. So the way to understand fusion, maybe a bit disappointingly, is that it's as an effective field theory. So differently than the fusion of local operators, the fusion of lines is best understood as a multiple expansion. We knew this from QED. So what does it mean? It means if I take two lines, I can generically approximate in the most conservative terms as a sum over other lines C. But this sum will not be conformal lines. So what does it mean? This means that from the low energy viewpoint, it will be a sum of infrared stable lines perturbed by all possible operators. So this sum here is all possible irrelevant perturbation on top of the line, and the coefficient up front is fixed simply by dimensional analysis of scale invariance. In fact, for more general contours, you have to use the full power of wire invariance. And let me also say that I'm being a bit schematic. What should appear here is not the angular distance, but it's truly the geodesic distance. But to the first leading orders, this difference doesn't really matter. When I say that all the operators on the line should be generated, it means that you should also generate a cosmological constant terms for all lines. By dimensional analysis, the cosmological constant term should be proportional to the inverse distance between the lines. This is nothing but the Casimir energy. So is this formula more or less clear to people? Now, in general, unless there are degeneracies between Casimir energies, the defect, since you understand this as an effective field theory, the idea is that you can compute the expectation value of these two lines, or correlation function representing two of two lines, in an EFT at small theta. But because of the Casimir energies, these are essential singularities at small thetas. So the idea is that only the smaller Casimir energy should be retained. Only the defect with the smaller Casimir energy should be retained, at least in the simplest setup. So this means that this is actually even best approximated as a sum without a sum, but of a single defect 0. Irrelevant perturbation. Schematically. Okay, so the idea is that you have two defects, they fuse and at small theta you can think they fuse in a single defect. This is just because all the others are way suppressed in theta. And therefore, in the small angle limit, the cusp anomalous dimension, which is just the energy of these two defects, a small distance, is dominated by the Casimir energy of the leading defect. Now, since this is a single defect insertion on the cylinder, this maps in flat space to a defect that connects the origin to infinity. So it maps to the defect creation operator. So it means that there is an extra term here, which is the ground state energy for this defect on the cylinder with a single insertion, which by the state operator correspondence is the scaling dimension of the operator that creates the defect. Plus, the first irrelevant perturbation will dominate the correction. So, plus dot dot dots, of course. Is the argument clear so far? No, but there is no, the point is that only the smaller Casimir energy, so there is no summing. So, as an immediate small application, if we take this, if we take B to be equal to, if we take for B equal A, the concavity that I showed before implies immediately that the Casimir energy between A and A bar is negative. So I write 1 because generically the diffusion of A bar contains the identity. It's not, well, not always, sorry. C A bar bar C, let's call it C. It's not always, sorry. So this is a very physical fact. It tells you that opposites attract. You take a defect, its orientation reversal, the Casimir energy is negative. So this is not a new result, of course, by no means. This is, I think, the first proof appeared in this paper by Bacchus, the first, at least, field theory proof in this language. And use somewhat different arguments, but they are still based on reflection positivity, of course. But I think it's cute that this cusp anomalous dimension, which can be used to prove something interesting about observables in flat space. Another highlight of this formula that I want to mention, which has also been noted by Peter and collaborators, is that the next term in this expansion is very interesting. So it is often the case that we're interested in studying diffusion of defect. That's a physical thing. We want to understand, when you put two defects close, what you should approximate with. So if you're able to compute the cusp anomalous dimension, then you'll get as a benefit this defect, the scaling dimension of the defect creation operator of the fused defect. And generically, bearing the generacies, this will give you strong information about diffusion. For instance, an exercise that you can do in an equal function Lagrangian means is to see that at strong coupling, the theta to 0 term in the cusp anomalous dimension is 0, strongly hinting the diffusion of a fundamental and anti-fundamental results in the singlet. Yes? When you allow some more, I think the problem, so let me think for a moment. Some local operator sitting on the cusp. I do expect that in general you will not be sitting on the ground state. Well, and in this formula, I'm not sure. Maybe Peter has more comments. And I'm not sure what it changes in this small angle formula. I think you might not be sitting on the ground state, but that sounds non-generic. Huh? The singlet term will change? That doesn't sound... I don't think that's possible, right? No, I'm not sure. I'm not sure. You might, if you fine-tune the operator you put, you might not be sitting on the ground state of the fused defect. Yeah, I think in general the picture is that you have this two
Yeah.
Yes. Yes. Right. Yeah. Yeah. Yeah, yeah. And I don't think it changes much. But of course, concavity in that case doesn't work anymore because then I would be considering a 4-point function of the displacement. So so the concavity property argued would fail there. At least it's not as obvious. I'll just put it like this. For the same reason why it fails for different defects. I mean, with the ground state, I think it's. I mean, I think it was roughly what I was saying here, right? So that you get. So here you get this defect change. You get this defect changing operator. Well. Yeah, but okay, but yeah. Well, you're saying because I think I'm just okay. I think you're right. I'm using secretly the. Sorry, I think you're right. So actually, in this case, it might still work. The reflection positive. I think I'm using reflection positive of this 4-point function. I can still insert a complete set of states. So.
Well, I'm just saying that whether there is a non-trivial, like my point is that you cannot have a trivial insertion in the cusp.
There is not a trivial insertion. That's why I have this formula here. Otherwise, I have this delta min is non-trivial.
Like when you're saying that you use reflection positivity, you're drawing this cut, right? But the cut passes through the cusp. So isn't that like trying to prove a positivity of a 3-point function by drawing it?
No, but I think on the cylinder, okay, I don't really like, it's not exactly this cut, but on the cylinder, you're kind of cutting like this, right? So it's I think it's a reflection positive of 4-point function secretly. It's a 4-point function, this, because I have an insertion at infinity and one here. It's not a 3-point function.
Sorry, so. But you made this argument here, right? It was the.
Yes, but I mean.
All right, but how? Okay, so then I can use even the same picture with the cylinder to try to prove the 3-point function of a scalar is positive.
I think with higher excited insertion it would be true, but it's not true for different defects because these two operators are not conjugate to each other.
No, that's fine. But maybe now I just have a question about your proof of the concavity, yes. Right? I'm just insisting that you are cutting. Like to use the reflection positivity, you have to choose where you cut the picture.
Yes.
And you're cutting through a singular point. So I'm asking, how is this proof better than trying to prove that just a bulk 3-point function is positive by cutting through one of the scalar operators in the 3-point function? So why can't I use this to prove that like 3-point function of epsilon has to be positive in Ising? Like, how is it different from trying to do that? Because on the cylinder, even with local operators, it could put one of the local operators at past infinity. So it's just hiding the problem, really.
Yeah, I'm secretly, okay. Let me just think for a moment. But it's not, it's a 4-point function. I think
so for instance, you might ask also why is reflection positivity working at all with defects even when you cut through like a non-singular point and okay, you use, it's part of the assumption of how the defect is defined, like how CFTs are defined. Imagine you have regularization, then you're saying, well, when I cut, I could discontinue the defect a little bit and then it wouldn't be an operator inserting where I cut, it would be like a state created in and a state created out. If you can do the same at the singular point, so this would make the ground state a bit special. Say you just have the defect that can end very close to the singular point, then that would be a reflection positive configuration. And I think it's part of the assumptions, yeah. So
I mean, in the cylinder picture, you would agree. I mean, what I'm computing, if you call this the ground state of the cusp, is something like this, and then I can insert completeness here. It's actually connected. I insert a sum over states, and you get on a manifest way a positive thing. I think that's from the flat space viewpoint, I agree. There is some assumption about this cap, which is related to the fact that I think I'm using a 4-point function. I don't have a better argument now, but.
I guess the point is that you can make regularization when you make for example, if you make the cusp smooth.
So I can make this very smooth. Yes, that's the idea. Yeah, I think that's the only way. But okay.
This shows that the ground state is special.
The ground state is special, yes, because the ground state is that one we approach by taking a smooth cusp. Thanks. Okay, so with time, how am I doing? 12:10. Okay. Okay, so the last, I guess, 10 minutes. How much do we have? 20 minutes. Okay, so this was all a bit abstract. So what? Okay, so the last thing, maybe 15 minutes or so. I don't want to take too much of your time. I just want to tell you some calculations we did to check all this stuff and review for you the localized magnetic field. Ten minutes. Okay. Okay. So as I said before, we are in the Ising model in D between 4 and 2. And this is your expression for the localized magnetic field. So, okay, let's see how much do I want to tell you. Okay, so let me first review a bit how this works in the epsilon expansion, and then maybe some comments about the fuzzy sphere work. So let me first focus on the defect fixed point. So the operator sigma for dimension close to 4, of course, is just a free field. So it means that it means that H is marginal in free theory, and it's going to acquire a small anomalous dimension at one loop. So you compute a beta function, you get a result, which is something like this, where this is the bulk coupling. And of course, if you draw a diagram, of course, you see that you have two fixed points which are all related by the Z2 symmetry. This is the beta H, and these are stable. So in a sense, the pinning field defect is the simplest defect you can think of in the Ising model, plus ... And at this fixed point, and this fixed point is stable because the scaling dimension of sigma on the defect at that fixed point is 1 plus epsilon plus ... which is larger than 1. Okay. Okay. So it's natural to study all I told you in this fixed point. And okay, so just to write a formula, the cusp anomalous dimension reads like this. So you have two cusps because you can take, say, this defect to be plus, and this here to be plus or minus, where plus or minus refer to the sign of the magnetic field. And you find this a very simple formula, 3-level. We did a one loop calculation. I will not bore you with it. Plus O epsilon, where this is evaluated at the fixed point. It's just for reference, H star is square root of 9. Okay. So the only thing I want to mention is the relation to fusion, which may be slightly more interesting. So what is the fusion of the pinning field of two pinning fields? So if I have a plus pinning field and a minus pinning field, you expect just by obvious consideration that this is going to result into a trivial defect. And instead, if I have a plus pinning field and a plus pinning field, this should be result again in a plus pinning field. Just because these are the only conformal defects you have, these two will annihilate. In fact, this follows by Z2, and this actually, again. So this is pretty intuitive. I think it doesn't require much justification. So we checked that the small angle expansion of our result agrees with this for theta to 0. For theta to 0, we find C plus minus 0 over theta plus 0 plus order theta. Okay? So the crucial thing is that the order theta to 0 term is 0. This is checked now one loop calculation, so including this order epsilon term, which actually is quite non-trivial because it turns out that the cusp anomalous dimension is way more complicated than in n equal 4 super Young Mills in this example. For the opposite defect, for the cusp between two equal defects, the result is a priori a bit puzzling, because you find an expression like this, plus constant, plus epsilon, some number, log theta. So the thing which is funny here is that for small angle, you find a logarithm of theta, but then you have to remember that in this theory you have an operator which is quasi-marginal of dimension 1 plus epsilon. So if you work hard and you use Kalman-Zimanzik, again, I'm not showing the detail, you actually find that the end result to one loop order again resums to something like this, delta plus 0, 1 man some number, which I don't want to write now, theta to the epsilon. So in the limit theta to 0, you are left with the expression you expect. So the Casimir energy plus a constant, which is precisely a defect creation operator, but you have infinitely many perturbations for the theta to the epsilon, theta to the epsilon, so forth, so on, because you have an operator of dimension 1 plus epsilon on the fused defect, and you can insert it infinitely many times. That's why you have this coefficient. So these are non-trivial checks of these formulas that I discussed before. Okay, questions here? Theta of constant times epsilon. No, it's theta to the epsilon, because so if you now expand, you have a theta to the epsilon, which is an insertion of this operator in conformal perturbation theory. Then a theta to the 2 epsilon, which is twice inserting the operator, which is irrelevant twice, and so forth, so on.
Are you saying that the constant in front of the log is exactly the same as
no, there is a number here. I'm not writing these numbers. There are some zeta numbers, whatever.
But if there's some ratio, it should be something like
no, but okay. I'm telling you to trust me that if you look at this number carefully and you use Kalman-Zimanzik carefully, you get theta to the epsilon. I'm not explaining. This is not obviously this. This is a non-trivial check of the formula.
I see. Thanks.
So this is not an obvious calculation. Well, not complicated, but yes. That I'm inserting twice the irrelevant operator.
Wouldn't that be theta to?
So the question is, what's the interpretation of theta to epsilon term?
So the irrelevant operator, the action for the irrelevant operation is something like theta to the epsilon, integral d tau of sigma hat. I call it sigma hat, sorry. Okay? So whenever if I lower it once, I have theta to the epsilon. If I lower it twice, I have theta to the 2 epsilon.
You mean it's like higher orders?
Higher order in conformal perturbation theories, yes.
I see, okay.
And you have to resum all of them, but since it's almost free, you can do it with standard RG methods. Okay, so let me close. Having checked these formulas, we can now apply them to the D equal 3 Ising fixed point with fuzzy sphere. So we had courses about this past year, so I will not say too much. But the amazing thing is that, let me just say that fuzzy sphere just realizes the Hamiltonian of the Ising model on a sphere, and all it has to do is to add two impurities on the sphere at distance theta, and then can simulate this cusp anomalous dimension just by state operator correspondence. And I won't be able to plot exact numbers. Pi, 3 pi over 10, something like this. So there is some plot in our paper that you can check. It's something like this. In this limit here, it agrees with the expectation from the theta close to pi expansion. And by fitting this tail here, we can extract the Casimir energy of two pinning field defects. Let me say that for the fuzzy sphere, it's very hard to go to small angle. So having this conformal perturbation theory expansion of the cusp anomalous dimension is very important. So here, what you do, you have this number, and then you fit with the formula I showed before, Casimir energy over theta, plus the defect creation operator scaling dimension, which was measured before by fuzzy sphere again. So it's something like, I think 1.0.12, something like this. Plus, here you put a coefficient that you have to fit, and the scaling dimension of the first irrelevant perturbation, where again delta sigma Attis was measured before and is known to be 1.6 roughly in 3D. And you get an estimate for the Casimir energy C++, which is negative as expected. And by the same method, you can also measure the Casimir energies between opposite defect, which is something like 1.4. So these are, I think, very nice results because these are potentially measurable. They're obtained with this fuzzy sphere method and combined with this expansion that I discussed before. So I don't know what I wrote here. Delta plus 0 should be this one. And yeah, so also the plot, I should say, is manifestly concave, so it agrees with the theory I discussed before. And I think this is a good moment to stop.
Some more questions to Gabriel? No questions? Oh.
Do you know if there's actual ongoing effort to measure these numbers, or how would you do it in a... Because a physical system like the magnetic field would be localized in a few lattice spacing, so you need to keep them far apart, you need to do some scaling.
Yeah, so I think actually a more measurable impurity would be some... So this impurity is very hard to realize in physical system. As you know, Francesco Tordini, this idea of realizing with colloidals, but that's very far-fetched. One application of this number would be, I think, more physical. In the O3 model, you can realize spin impurities. That actually you can do, just put doping atoms. And we argued, in one of my former papers that spin impurities reduce to localized magnetic field in certain limits. And I think there would be measurable. To actually realize a localized magnetic field in experiment, I agree it's very hard. So it's a bit more, it's more because of kind of a hydrogen atom of defects in strongly coupled theories, the pinning field. That's why it's interesting.
Any questions? Okay, if there are no more questions, let's thank Gabriel again.